Let's now look at graphs of functions. We know that we can define a function using an equation. We can say, let's define a function as f of x is equal to something, 2x plus 5, 9x squared, x to the third power. There's different ways we can define any function, right? Whenever we have a function, what we have is a collection of ordered pairs. And that collection of ordered pairs, anytime you have an x value, it's associated to a unique y value. It's a unique result. What that means is we can graph these solution sets. We can graph the set of solutions to this equation and have a graph that represents that function. Now, there are lots of different function types, and so there's lots of different graphs. But if you know what some of the basic graphs look like, that can help a lot in finding the graphs of more complicated graphs. What we're going to do right now is we're going to look at some very basic graphs, and we're going to see how those can help us find the graphs of things that are a bit more complicated. So when we graph an equation, the first thing we want to do is we want to think, what type of function is this? Okay, well, what are the types of functions that we have? Well, there is what's called the quadratic function. Now, this is not the only quadratic function that exists. I misspelled that. Quadratic, T-I-C. There we go, quadratic. This is not the only quadratic function that exists. Rather, this is the simplest quadratic function that exists. All right? So, every other quadratic function will be a more complicated version of this one. Okay, so what does this one look like? Well, the way this one looks is it is a parabola. It's kind of like a U shape. It's going to cross through 0, 0. It's going to go up and to the right, and it's going to go up to the left as well, like this. This shape is called a parabola, and every time you have a quadratic function, it's going to look kind of like this. So if I'm graphing f of x equals x squared, well, that's this graph right here. If I'm graphing anything else that's this type of function, when we say this type of function, we mean things that have a square on them as the biggest power, then the graph is going to look like this, but modified. Maybe we're going to have to move it over a little, or maybe we're going to have to move it up, or maybe flip it upside down. We're going to change it, but we're still going to have this basic shape. Right? So this allows us to focus on just a few points, and that is sufficient to give us a full graph. We'll see that here in just a moment, but first let's continue on with some more very basic functions. F of x equals x to the third. So if the biggest power is a second power, that's called a quadratic function. But if the biggest power is a third power, that's called a cubic function. And the graph of the most basic cubic function, again, not every cubic function looks like this, but they're all in the same category. They're all the same type of function, which means they all look similar. The most basic cubic function is going to look like this. It's going to go up to the right, going through the origin, so a lot like this one did. But instead of going up to the left, it's going to go down to the left, this way. And anytime you have a cubic function, its graph is going to look something like this one. This is the graph of x to the third. But every cubic function kind of looks like this. Okay. The next one we're going to look at is the absolute value function. F of x equals the absolute value of x. And this is called the absolute value function. And the shape of the absolute value function is a lot like the parabola, but the lines are straight instead of curved. So the absolute value function is going to cross through the origin. It's going to go up to the left and up to the right. But instead of being this bowl shape, this parabola shape, it's going to be a straight line in either direction, sort of a V shape, like that. So this is the most basic absolute value function. And if you had another function that was of this category, meaning something with absolute values around it, it would kind of look like this, modified a bit. Okay. The next one we're going to look at is the square root function. F of x equals the square root of x. We're not all original when it comes to naming stuff. This is called the absolute value function because it's a function that has an absolute value. This is called the square root function because it's a function that has a square root in it. The square root function looks like this. It's going to start at the origin. Notice they all do the same thing. They'll start at the origin. This one's going to go up to the right, but instead of going up and get steeper like this one, or instead of going up as a straight line like this one, it's going to go up and start to flatten out. So kind of like this. Okay. And what about to the left? Well, nothing happens to the left. Because remember, if you're going to take the square root of a number, you're always going to get a positive. All right, so you're not going to have anything down here. And taking the square root of a negative number doesn't give you any real number. All right, if you take the square root of a positive number, you can only take the square root of a positive number and get a real solution. Because, of course, if you square a positive, you get a positive. And if you square a negative, you still get a positive. So you can't square any real number to get a negative, which means that the square root of a negative isn't going to yield us anything on our graph. All right? So here it's only this part. Finally, we're going to look at what's called the, depending on what book you're looking at, it's either called the inverse function, the rational function, or the reciprocal function. So here I'm going to settle on the name reciprocal function. However, there are other names for it. Here you're saying the reciprocal of x. The reciprocal function is the only one that doesn't go through the origin. However, the origin does still play a role. The shape of the reciprocal function is like this. It's going to go along both of the axes. It's going to go up along the positive y-axis, and it's going to go out along the positive x-axis. On this side, it's going to do the same thing, but in the other direction. It's going to go out along the negative x-axis and down along the negative y-axis. Okay? So here, notice this doesn't ever touch either of the axes. It just sort of travels alongside of the axes. That means that there are two straight lines which the graph never touches. In more advanced classes, those are called asymptotes. That's not really the formal definition. The definition of an asymptote isn't a line that a graph never touches, but visually that's what they look like. Your graph doesn't touch the asymptotes. We're not going to go into full detail as to what those are. Right now, we're simply going to stick with the visual. We're going to say, with the reciprocal function, you can imagine that these two lines are never touched by this graph. It follows alongside of them, but it never actually touches them. Notice that the two lines that the graph follows cross where? At the origin. So even here, the origin plays a role, even though it's not part of the graph. These functions are not exactly special. Rather, they are simple. These are simple versions of more complicated functions. But knowing just a few basic functions can help you graph much more complicated functions. So let's see an example of that. Let's say, for example, we're going to graph, let's see, what do we want to graph? Let's go with 9 minus x squared. Okay, so there's a lot to do here. Because whenever you graph something, what you normally do is you find individual points and then connect. With a linear equation, that works very, very well, because all you need are 2 points. And when you connect 2 points, that forms a line, and you're done. But notice this is not a linear equation, because in a linear equation, you don't have any powers greater than 1. Okay? So you say, all right, well, then let me just plot some points and connect those dots. How hard could that be? The problem is that if all you do is graph individual points, it's hard to tell when you're done. For example, if these are 2 dots right here, if these are 2 solutions to my equation, and I told you graph that, you would say, well, sure, of course I can. I just draw a straight line through those, right? And what if I tell you, well, the graph's not supposed to be a straight line, though? Well, then what's it supposed to be? Well, I don't know. I'm not sure what my graph's supposed to be. So at this point, you say, okay, you know what? Let me just graph a few more points. All right, so let me graph a few more points, and right there. Here we go. I graphed 4 points. Now, I'm pretty sure that's a line, right? And I tell you, no, it's not a line. You say, well, what else could I graph through those points? That's not a line. Well, I could do this. Right? Or I could do this. No one said it had to be a straight line. I could do this. Like that. All of those are curves. They're all graphs that pass through those 4 points. So if I don't know what my graph is supposed to look like, I'm not really sure when to stop. Are 4 points enough? Well, maybe, maybe not. Are 5 points enough? 10, 50, 100? Well, the answer is I don't know. If I don't know what my graph's supposed to look like, I don't really know when I'm done. That's what this is for. Notice, what I'm trying to graph is 9 minus x squared. Here, notice that this has an x squared in it. There aren't any bigger powers than that. That's important. Because up here, I have the most basic function with a square on it is the y equals x squared. It has this graph. Now, I notice this one also has a power, but that's got a power of 3. This one doesn't have any powers of 3. It's just power of 2. So what that means is I know my graph fits into this category. It's a quadratic function, which means that my graph is going to look like this. Now, it's probably not going to look exactly like this. In fact, it's definitely not going to look exactly like this because it's not the same function. But they fall into the same family, right? They're of the same category. So here, with that knowledge, the fact that my graph has to look like a U shape, now let's see if we can't graph this. I'm going to plot a few points. I'm going to say, all right, let's set x equal to, let's just start with 0 and see what happens. If we set x equal to 0, well then f of 0 is equal to 9 minus 0 squared, which is just the number 9. Okay, so that's one solution, 0, comma 9. What if I set x equal to, let's just say positive 1. Okay, in that case, I can say f of 1, that's equal to 9 minus 1 squared, which is, well, let's see, that's 9 minus 8, 9 minus 1, which is 8. So that's 1 comma 8. Let me do just a couple more. Let me use a negative number. Let's say x equals to minus 1. All right, well, that's going to be f of minus 1, which is 9 minus a negative 1 squared. Notice squaring negative 1 is still a positive. Okay, so it's going to be 9 minus a positive 1, which is 8. So negative 1 comma 8. Okay, and let me do one more. Let me set x equals to, I don't know, 3. F of 3, that's 9 minus 3 squared. I guess I should put all these in parentheses, right? The numbers I'm plugging in. There we go. 3 squared is 9. 9 minus 9 must be 0. So that's a 3 comma 0. All right, so now, here I've graphed 4 points. Just like up here, I had 4 points. But before, those 4 points weren't really going to be useful because I didn't know what my graph was supposed to look like. But now let's see what happens with just a little bit of knowledge about the shape of this graph. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3, 4, 5. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. All right, so let's go ahead and plot these points. 0, 9, that's going to be up here. Don't go left or right, go up by 9. 1 comma 8, that's 1 to the right, up by 8. Negative 1 comma 8, okay, that's left 1 up 8. And 3 comma 0, that's 3 to the right, and then don't go up or down at all. All right, so now we're going to connect the dots. But we know what the shape's supposed to look like. Whatever those dots are, whenever we connect them, they have to form a shape like this. They have to form sort of a U shape, a bowl shape. Oh, well, if I connect those dots, sure, I can do that. And there we go. Just a few points is enough to give me a graph. Notice I didn't connect, if I didn't know better, I might have connected them like a V shape. Hey, look, I could have drawn a straight line through those, and I could have drawn a straight line this way. I could have done something a little wavier, right? I could have come from down here, gone up, hit that point, and then gone back up. Right? There's lots of choices that I could have, well, there's more choices if I actually draw this straight, right? There's lots of choices that I have, but by knowing ahead of time what the graph is supposed to look like, that narrows it down significantly. So that just a few points is enough to give me a good graph. Right? So if ever you see something that has an x squared as its biggest power, you know the shape's got to be like that. And well, here the shape is upside down, and it's a little higher than it was up above, but it's still the same basic shape. If you have x to the third, the shape's going to look something like that. If you have an absolute value, it'll look something like that. Square root, it'll look something like that. Okay? So go ahead and give this a try. I'm going to go ahead and give you a function to graph, and you're going to graph it by plotting a few points. You don't need very many though. You need just a few, because what you're going to do is you're going to use one of these to tell you what the shape of the graph is supposed to be. And then with just a few points, you'll be able to create the graph. All right, so let's go ahead and have you try one of the following. For example, let's have you graph. Oh, let's see. What do we want to go with? Let's go ahead and try graph f of x equals the square root of 4 minus x. Now remember, you're going to compare that to the 5 basic ones that we saw over here. Which one is that one most like? Okay, once you know which one it's most like, which one it resembles, go ahead and figure out, okay, that's the shape of that graph. And then you're going to plot a few points, and using those few points along with the shape that you know the graph's supposed to look like, you're going to go ahead and complete the graph. So give that a try now. Go ahead and pause the video. Oh, I guess I should label that as a, let's see, go ahead and try that. Go ahead and pause the video, give that a try, and once you're done, go ahead and unpause and we'll go through it together. All right, so I see a square root, and here, that means that's going to be of this category. It's going to be a square root function. Again, we're not at all clever or original when it comes to naming stuff. It's called a square root function because there's a square root in it. So I know my shape has to look something like this. Now, it won't be exactly this, but I have a rough idea as to what the shape is supposed to look like. It's supposed to start somewhere and then go off in some direction, but not straight up. It's supposed to flatten out a little. Okay, so let's go and do that. Let's plot a few points. You may have plotted the same points that I'm about to, or maybe something different, but usually you want to just use small, simple points, small, simple numbers. All right, so let's go ahead and give that a try. Let's go ahead and find f of 0. All right, so square root of 4 minus 0, that's the square root of 4, which is 2. 2 squared is 4, so square root of 4 is 2. All right, now, f of 1 isn't going to give me a nice number here, is it? Because 4 minus 1 is 3, and I don't know the square root of 3. And I'm not out of calculator right now, so that one's going to be a little hard to work with. So I think I'll skip 1. Same thing with 2 and 3. I don't like those, right? Because actually 3 works pretty well. 4 minus 3 is 1, and I can do that. All right, so I'm going to give that a try. F of 3, that's the square root of 4 minus 3, which is the square root of 1, which is just the number 1. Okay. And I can try f of 4, and that's going to be square root of 4 minus 4, which is just 0. Let me try a negative number. All right. Here I've been doing all positives. It's a good idea to try at least one negative. So let's see here. I guess I'll do it over here. F of, again, let me not do a number that's going to be hard for me to work with. So let's see. If I try negative 1, minus a minus 1, that's the same as plus 1. So 4 plus 1 is 5, and I don't want to take the square root of 5. Square root of 6, that doesn't work nicely. 7, 8. Oh, square root of 9 works pretty well, because I can take square root of 9. That's 3. So if I use the number negative 5, 4 minus a minus 5, or in other words, 4 plus 5 is 9. And if I take the square root of 9, that's the number 3. Okay? Now, if you used other numbers besides these, it'll still work. It'll still give you the correct graph, but those numbers are harder to work with because I don't want to graph the square root of 3, especially when I'm not allowed a calculator. It's hard to tell square root of 3 is exactly what number. Well, I don't really know, right? But here, these numbers are easy to work with. All right, so let's go and graph this. Normally, graphing just with a few points is not a good idea because, well, you don't know what the graph's supposed to look like. But we do know what the graph's supposed to look like. So this should be plenty of information. All right, so let's see here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, and 5. All right. My points are, now remember I plugged in 0 here and I got 2, so 0, 2. 3, 1. Okay, so 3, 1, 2, 3, 1 right there. And then I plug in 4 and I got 0, so 4, 0. So right there, 4, 0. And then over here I've got, if I plug in -5, I get +3. So 1, 2, 3. So we know what this graph's supposed to look like, right? It's supposed to have this kind of shape. It's supposed to start somewhere, and it's going to go up and kind of flatten out as it goes up. So if I connect those dots using that pattern in mind, I can start from here, and I'm going to go up. Notice I'm going to go this way now instead of the other way like the first picture. But it's still going to follow the same pattern. It's going to go up and kind of flatten out. And it would help if I drew that a little cleaner, right? There we go. And there is my graph. Well, what can I say? I teach math, not art, but that didn't come out quite so well. It's supposed to have that sort of curving shape here. It looks a little straighter than I intended it to, but it's the what's it saying? It's a thought that counts. That starts from here and it goes up and curves a bit. Now, while there are many functions, not just the ones that we've seen here, but there are other categories which we don't worry about here. There are tens of hundreds of thousands of different types of functions. However, there are 3 functions that we see much more often than any others because of how common and simple they are. So let's go ahead and define those. Let's begin with let A, B, and C be real numbers where A is not equal to 0. And, I guess I'm missing one. I need one more. Let A, B, C, let's do one more. In fact, let me just write it separately. Let M also be a real number where M is not 0. Okay, so A, B, and C are real numbers, so is M, and B and C can be anything, but A and M should not be 0. They can be anything else, just not 0. In that case, a constant function, oops, I wrote that too close together. Let's try that again. There we go. A constant function is a function of the type f of x equals b. So here, a constant function is, remember, b is just a real number. It can be anything. It can even be 0. A and M can't be 0, but b can be 0 if you want. Okay, so a constant function is a function of the type f of x equals to a constant number. So for example, f of x is equal to 12, f of x is equal to 9, f of x is equal to 0 if you like. The graph of any of these is going to be a horizontal line. Okay? A linear function, and we've seen lines before, a linear function is a function of the type f of x equals mx plus b, where, again, m is a real number that's not 0, so this can be any number except 0, and b is just some real number. It can be anything, including 0. Okay? The graphs of these are all slanted lines. If m is equal to 0, then this goes away and you're back to a constant function. So that's why we say m should not be 0, because if m is 0, that's not really there. Okay? And then the third one is the quadratic function. And I showed you one example of a quadratic function, or actually two of them, right? I showed you the simplest possible quadratic function, and then I showed you one which was a little more complicated. The most general form of a quadratic function, the most complicated possible one, a quadratic function is a function of the type f of x equals ax squared plus bx plus c, where again a should not be 0, but b and c can be whatever. So here, as long as this is still here, that's considered a quadratic function. If a is 0, well then that goes away, and now that looks like a linear function. All right, bx plus c, it's kind of like saying mx plus b. Same thing, number x plus number, number x plus number. So here we want to make sure this one is not 0. That's why we say, oh, let's make sure a is not 0. So a constant function has a graph that is a horizontal line. A linear function has a graph that is a slanted line. Again, if the slope is not 0, the graph is going to be diagonal. And the quadratic function is going to have that parabola shape, as we saw a moment ago. Constant, flat, linear, diagonal, and quadratic is a parabola. And I keep saying that word, I should probably label that. The shape of this, that sort of U shape, that's called a parabola. Like that, parabola. These functions are ubiquitous. They occur a lot in math, and especially in applications, because they're often used to model different behaviors. They're often used to model different situations. One of the useful things about a model is that it allows you to summarize a lot of information, and it allows you to pick out important pieces of information that might otherwise be more difficult to find or to summarize. One of those pieces of information is the intercept of a graph. So let's go ahead and define what those are. Definition. Let f be a function. It doesn't matter what function, just a function. Let f be a function. Then the point 0, comma f of 0 whenever x is equal to 0, and whatever you get when you plug in 0 into that function, that's got to be your y-intercept. Okay. Along with this definition, let's talk about the x-intercept. Again, let's go ahead and let f be a function. Then the point x, comma 0 is an x-intercept. For all x such that f of x is equal to 0. Okay? Meaning, okay, find any number so that if you plug it into x, you plug that into f, you get 0. Okay, let's say you find one answer like that. Let's say you find one number that makes f 0. Oh, well, in that case, it's that number, comma 0. That's your x-intercept. Let's say you find two answers like that. Okay, well then there's going to be two different x-intercepts. That's why I say an x-intercept, because there can be more than one. But for a function, there will only be one y-intercept. That's why I refer to it as the y-intercept. There's going to be only one. Okay, the y-intercept, if you think about it graphically, it's where it crosses the y-axis. So here, note graphically, the graph crosses the y-axis at the y-intercept. And the x-axis at the x-intercept. All right. So now there's two ways to think about this, and again, that has to do with either the algebra or with the graph. So let's do an example of each. Let's begin with one example. Let's go ahead and find the x and the y-intercepts. Y-intercepts of the function, and here we'll use a linear function f of x equals 3x minus 5. Okay, so now the y-intercept is usually the simple one because all you do is you plug in 0 in for x and then do the computation. So here for the y-intercept, you're going to start by saying we're going to set x equal to 0. That's going to mean we're going to find f of 0, which is 3 times 0 minus 5, which is just negative 5. So that number, that's your f of 0, that's negative 5, which means 0 comma negative 5, that's your y-intercept. So here your y-intercept is 0 comma negative 5. When you plug in x is equal to 0, your y is negative 5. So take that 0 comma that result, that negative 5. What about the x-intercept? Well, depending on the problem, finding an x-intercept can be very simple or very complicated or somewhere in between. For this example, we gave something simple, and for now, we're going to stick with only simple things. However, anyone who goes into a more advanced class, if you go into a college algebra class, if you go into trigonometry or higher, then finding an x-intercept can be very, very challenging to the point where there are entire chapters of algebra books, and in fact, there are even entire books dedicated to showing you exactly how to find the zeros of a function. But we're not going anywhere near that deep. For us, we're dealing with relatively simple equations, right? Linear, constant, things like that. Right? So we want to find these x values because we know that's going to be the number 0. Okay, what x value do we want? Well, we want all the x's so that if we plug those into the function, we're going to get 0. Okay, so if we're looking for the x, well, if that's the x, what's that 0 represent? Well, that's got to be your y, doesn't it? So here, for the x-intercept, we're going to set y equal to 0. Okay, so let's do that. Here, that's f of x, that's like saying that's your y. So 0 equals 3x minus 5. Notice that for the y-intercept, you're plugging in a 0 into just the x. For the x-intercept, you're substituting the entire f of x as 0. All right, you're setting your y equal to 0. And now this can be solved. When you go and add 5 to both sides, that makes that a positive 5, and that makes that negative 5 go away. And then let me divide both sides by 3. So we get 5 over 3 equals to x. And that's it. That's the only solution to this equation. There's only one x value, which makes this thing equal to 0. Okay, well, there we go. We found all the x's. Now, if there was more than one, well, there's more than one. But in this case, there's only that one. We found all the x's such that if we plug in that number into the function, we're going to get 0. Okay, so that's my x, which means that my x-intercept, there's only one, and it's going to be 5/3, comma 0. And there we go. There's our y-intercept. We find it by setting x equal to 0, there and there. We find the x-intercept by setting y equal to 0, which is that number there. And those are our results. The other way we can look at this is graphically. Because again, what we're looking for the x-intercept is where your graph crosses the x-axis. Now there can be one or more than one. Well, here we can find the y-intercept where the graph crosses the y-axis. And again, there can be one, and there can only be one of those. So let's consider the following graph. So in this graph, we can also ask for the x-intercept and the y-intercept. Notice in this case, there's more than one x-intercept though. Here we do only have one y-intercept. It's the only place where your graph crosses the y-axis. We know that a function can only have one y-intercept because the y-axis is a vertical line. And by the vertical line test, that means that the vertical line can only cross the function one time. If it were to cross more than one time, this wouldn't be a function anymore. All right, so because of the vertical line test, because we know that a function cannot cross any vertical line more than once, that means we know for a fact that the y-intercept has to be unique. There can only be one. Now, it's possible there's not any. You might not ever cross the y-axis, but you can't do it more than once. The x-axis, however, is not necessarily unique. You can have more than one. In this graph, you notice you have this one right here. Let's start from this side. Let's see, that's between 4 and 6, so that's got to be 5 right there. So 5, 0 is one of my intercepts. Another one right here, 3, 0, halfway between 2 and 4. Here I made this graph. There's no ambiguity here. If it looks like 3, it's 3. I'm not going to say, oh no, sorry, that's 2.9. So here that's 3, 0. That's 5, 0. Over here I got negative 2, 0. And right here I got 3, 0. It looks like the 4 got cut off on my picture here. So that's 3, 0. Notice that I have only one y-intercept, and that's 0, 2. When you have the graph of something, notice how much simpler that is to talk about the key points. Here, we don't need to go through the algebra because all of the information is already summarized. Without having to go through and solve for any variables, without having to go through and substitute any values, we instantly see, hey, there's 4 intercepts here on the x-axis. Negative 3, 0, negative 2, 0. Positive 3, 0, and positive 5, 0. And there is only a single y-intercept at 0, 2. So using a graph is a wonderful way of summarizing information so that we can pick out key features. In applications, a single graph will often tell you everything you need to know about that situation to get you a result. Or at the very least, it gives you enough that you know what to do to finish getting that result. And that is it for now. If anybody has any questions, comments, problems, please make a note of those and reach out. Let me know what I can do to help you. And I hope everyone has a nice day.